In this video, we're going to learn about the logistic growth function. And what I'm going to do is I'm going to start off by explaining and showing the differential equation and the solution to the differential equation, or the formula for logistic growth. Following that, I'm going to derive the formula. It's a bit of a mess. If you don't need it, don't want it, skip down to the example. I'll have links in the description below. So let's dive right in. Logistic growth function is basically a way to model population growth where there is some max population. I like to consider this as sort of the zombie example. So we have time and we have number of zombies. And of course, you always start off with a very few zombies. And in the very beginning, the number of zombies will grow very slowly because there are very few zombies to pass on zombieism or whatever. So it's going to grow, but very slowly. But as it grows, there are now more zombies to create more other zombies. So it grows faster and faster and faster to a point. But here's the problem. You already need people to turn into zombies. So at some point, the biggest limiting factor is not the number of zombies, but the number of remaining people. So once most of the people get turned into zombies, now it's going to be harder and harder for the zombies to find people to turn into zombies, and the trend is going to level off again. It won't be exponential. It will level off and trend towards some asymptote here, which is probably the number of people that were around to begin with. So sometimes people think of population growth to be exponential, but in most cases there's this limiting factor. Whether you're talking about a rumor being spread in a school where when no one knows the rumor, it grows slowly, or when very few people know the rumor, it grows slowly. When a lot of people know it and a lot of people still need to know it, it grows quickly. But then when almost everyone knows it, when two people talk about it, no one is learning about it new. So here's the way that it is modeled. The change in the population with respect to time will be equal to some constant rate times the number of things in the population times 1 minus p over m, where m is the maximum. So if p is exceptionally small, then this will be small because we're multiplying by a very small number. The closer this is to 0, the closer this is to 0. If p is close to the maximum number that it can hold, then this will be close to 0, and so this will be close to 0. So you can see that the rate is going to be low here, the rate is going to be low here, but there will be some sweet spot where p is relatively large, but still not close enough to m to make this approach 0. So let me label these variables for us. P is the population. T is time. R, I'm just going to mark it's just some constant. It's not really the rate because this isn't linear, the rate's going to be changing, but it is true that a larger R value will make it go through this cycle much faster. A smaller R value will stretch out the time it takes to get close to our maximum. M is sort of our maximum carrying population. So how much whatever the situation is can hold safely. In the real world, a lot of things might go past that. So if you have population on an island of rabbits, eventually they'll grow so quickly that they will have more than the island can support, and they will die off due to disease or lack of resources. And one more thing here is P naught, which is basically the starting population. So this is the differential equation. here's the solution, which is basically like the formula. And it's a mess. P equals m p naught e to the RT all over m plus p naught e to the RT minus 1. So the next slide or two will be me showing how to get from here to here. It's a mess. If you don't want to see it, you probably don't need to see it, but if you're like, I need to see this for something, let me derive that. So we're going to start with dp dt. I should probably be writing on here, dp dt equals r p 1 minus p over m. I need to separate the variables, so I'm going to move all the stuff with p over there and move the dt over there. So I get dp over p times 1 minus p over m equals r dt. Now, I want to take the antiderivative of this, but it is currently a mess. So what I'm going to do is I'm going to use partial fractions to rewrite 1 over p 1 minus p over m as two fractions, a over p plus b over 1 minus p over m. And the method for that is I will multiply them by the missing factors. So I will multiply this to a, and I'll get a minus p over ma. And I'll multiply this to b and get plus pb. And all this has to equal this value of 1. And the only term here without a variable, notice this doesn't have variables a, so I know that a must equal 1 from there. And then when I put 1 in, I'll get 1 equals 1 minus p over m plus pb. And subtract both sides, move this over. Basically, I'm going to get that b is going to be 1 over m. And bring it back in. So really, I'm looking at, let me just bring it over here, 1 over p, because a is 1, plus 1 over m, all over 1 minus p over m. Now, I don't like this fraction to fraction, so I'm going to multiply everything through by m, and when I multiply everything here through by m, that's really going to be, so let me just multiply this through by m, I will really get 1 over m minus p. And that's going to have a dp equals r dt. Take some antiderivatives. Antiderivative of 1 over p is the natural log of the absolute value of p. Antiderivative of 1 over m minus p, because the p is negative here, I'll get minus the natural log of the absolute value of m minus p. And the antiderivative of r dt is just rt plus c. Now, using my log properties, I can combine this as the natural log of the absolute value of p over m minus p. And I still have, sorry, not an e yet, rt plus c. To get rid of the natural log, I use a power of e. To get rid of the absolute value, I have a plus or minus, and this plus c could come out as a coefficient. So I get p over m minus p equals a e to the rt. And now I'm going to actually put in, switch this, the fact that the population at time 0 we will represent as p naught. So I know that p naught over m minus p naught equals a e to the r times 0, r times 0 is 0, e to the 0 is 1, so this is a. Let me switch to another slide. So we're sitting at the point now where we have p over m minus p is equal to p naught e to the rt over m minus p naught. All I have to do now is solve for p, which is just a little bit of algebra. So I'm going to multiply both sides by m minus p, and when this distributes, I will get p equals mp naught e to the rt over m minus p naught minus p times this stuff. I'm going to leave it separate because I'm going to have to factor it out shortly anyway. I'm going to add this to both sides to get all of the p's on one side, the variable p. So I get p plus p times p naught e to the rt over m minus p naught. And that's still going to equal mp naught e to the rt over m minus p naught. Let me change colors, just because I feel like it. So I'm going to factor out this p here and get p times 1 plus p naught e to the rt over m minus p naught. That will equal mp naught e to the rt over m minus p naught. I'll divide both sides by 1 plus p naught e to the rt over m minus p naught, and when I divide, it's going to end up in the denominator. So I will have p equals m p naught e to the rt all over m minus p naught times this whole mess. 1 plus p naught e to the rt over m minus p naught. But when this distributes through, it's going to cancel out that denominator, and so I get m p naught e to the rt. You can see it's starting to look more and more like what we want. M minus p naught times 1 is just m minus p naught, but m minus p naught times p naught e to the rt over m minus p naught is just going to be plus p naught e to the rt. And the last thing to get this to what we had is to factor p naught out of these two terms, and I'll get m p naught e to the rt all over m plus p naught. I have a positive e to the rt and a negative 1. Let's see an example. So in this case, I am given r. Let me mark that down. R is equal to 0.2. I'm given the p naught at year 0, so the starting population will be 12. And I'm given the maximum carrying capacity, in this case 250. So m is 250. Based on what we just saw, I can jump straight to the solution. So p equals 250, so m p naught, so times 12, e to the 0.2 t, all over m plus p naught, e to the rt, so e to the 0.2 t, minus 1. And let me think this through. So 250 times 12 should give me 3,000. So I get 3,000 e to the 0.2t all over, and I can leave it like this. I could distribute through the 12. It doesn't matter to me, so I'll just leave it like it is. 250 plus 12 e to the 0.2 t minus 1. And there is my equation let's look at the graph and see if it makes sense. So, in here, I'm going to put this in, so I need parentheses, 3,000 times e to the 0.2x, close that off, divided by 250 plus 12 times e to the 0.2x minus 1, close that parentheses, and then close another parentheses. And if I just had this, it's not going to be too useful. It's like, okay, it looks, I don't know, like an exponential growth function. The reason for this is I haven't seen enough. Notice these things max out at about 250 rabbits. I don't care what happens in the negatives, so I'm going to start at -1 so I can still see the x-axis. Let's go up to 20 years, see what happens in 20 years. But the most important thing is my maximum y should encompass 250. So I'm going to go to 260 here. And when I graph this, now it should look a lot more like what we saw. So we start growing very slowly, but then it grows faster and faster and faster. And maybe I didn't see everything I wanted. Let me go a little bit further to the right so we can really see this thing level off. So let's go up to 40. And now that I have this, I can easily answer a lot of questions. Like I could say, how many rabbits will there be after 30 years? Well, I could just trace when x is 30, not 60. And I'll see that there should be about 238 rabbits. Or I could try to figure out when there will be 200 rabbits by just graphing another line at 200. And then finding their intersection. So there's many things I can do now that I have this graph. So there's my first equation, there's my second equation, that's close enough for a guess, and we should get to 200 rabbits after almost 22 years. I hope this helped out. Feel free to comment below if you do have any questions.